Yeah, so today I'm going to talk about something that's just really exciting to me, and it's an open source product that we built at Stitch Fix. I'm going to talk about how you can build scalable feature engineering with Hamilton. So if I want you to take home a few things from today, I'm going to try to convince you something. First, I want to convince you that maintaining feature engineering code is difficult. It's because feature engineering code can often get into a loop where the maintenance of it costs more than the building of it. So you're kind of treading water. Hamilton, the framework we built, can help you escape that loop. And Hamilton is easy to get started with and easy to use. Cool. So first things first, Hamilton is open source code, real easy to install, real easy to get started with. You can install it in PyPy, it's also on Conda. You can get started in less than 15 minutes. We have plenty of documentation online and lots of examples. So this is probably the most important thing on the slide. All right, on the agenda today. First, I want to start off with a motivating story of data science pain. This is what we... Okay, yeah, this slide I'll switch it up again. You're good? Yeah, if you have any questions, you can interrupt me in the middle. All right, so on the agenda today, I'm going to start with a motivating story of data science pain. So I want to talk about why we created Hamilton in the first place, and sort of the difficulties the data science team at Stitch Fix is going through. Then I'm going to talk about Hamilton, the solution to their pain, and how we built it, sort of what its core principles are. Next, I want to talk about about sort of scaling up feature engineering and how it can help. And by scaling, I mean two things. I'll get into this later, but it's not just scaling in the compute and data sense. I'm really interested in scaling sort of the human and team component, making it so as the business gets more complicated, you can still maintain and manage these pipelines. Finally, I want to talk about open source progress and next steps for the pipeline. So let's dig into the data scientists who are suffering. But first, I'll give you a sense of the scene we're in, the company that I work for called Stitch Fix. It's an online personalized styling service. So there's sort of two ways to interact with Stitch Fix. You create your style profile, and this gives us sort of basic information about you and a good sense of what will fit you. Then a stylist, either you can go the sort of automatic subscription route, or the sort of personalized stylist choice, where they give you 5 hand-picked items that are tailor-made to fit your tailor chosen to fit you, and you keep what you like and send back the rest, and sort of an iterative process. You can learn from that. Or you shop at your own personal online curated store, check out what you like, you take it home, you can return it if you want. But the interesting thing about this, I mean, you might be like, okay, clothing, this makes sense, but why are you speaking at a data conference? Data science, though, powers every bit of the user experience, and it's all highly tailored and optimized. So selecting which clothes to show the stylist that you choose for you is all done by an algorithm. Optimizing warehouse patterns, predicting merchandise, and figuring out what to buy 6 to 12 months in advance. All done, powered largely by data scientists. And this has been incredibly successful so far. So we've got 100 data scientists and data platform engineers, all of whom work on optimizing the customer experience. I'm a data platform engineer, so I work on building the tooling out for data scientists. And you can see we've written about this quite a bit. I wrote a Hamilton post there, but we write everything from data science sort of applications and models we've built to data platform. We're trying to be very open out there. There's a few other things. If you Google, the blog is called Multi-Threaded. It's kind of cute pun. If you Google it, you can look and sort of read about how we approach things. All right, so I want to tell you about Stitch Fix's oldest model. Oldest is in the first one that they wrote, and until not too long ago, was still running in production. And this is the model to forecast the business. So if you want to decide what to do in a year, make plans for staffing, make plans for what to build, you're going to want to forecast how the business is doing. This is understanding where demand might be, where signups might be, where churn might be, and what sort of capacity you need to fill. And this is a fairly standard sort of time series machine learning problem. You've got your data coming to business actuals. Then you sort of process that, turn it into a featureized data frame, fit a bunch of time series models, predict the future, right? So use those time series models to run a simulation looking forward, and then generate out a data frame with a forecast, save that somewhere, that's your consumable artifact. So pretty standard thing. I'm going to focus in on the featureization side, right? The taking data from the business actuals and turning it into features that your model can read. This is actually all modeled in Hamilton, and you realize it's really meant to do this whole thing, but the featureized piece is what's interesting for this one. So the approach before Hamilton came in was a bunch of operations on a giant monolithic central data frame. So time was the key, columns were sort of like different signals you want to predict. And there were like 1,000 to 10,000 to maybe even more operations. A lot of configurations that was buried within business logic. So when you want to model a fairly complex business, you need to be able to sort of switch the way code can execute. So there were a lot of like nested if-else statements, a lot of functions that had sort of different behavior. It was all buried within the scripts, and multiple layers of scripts to execute, store, and visualize this data. And they had a world-class team of data scientists running this. So it worked fairly well, but what got them there, what got them from starting the business with zero forecasting ability to actually being able to forecast up to year in advance with reasonable accuracy, wasn't going to get them to where citrus wanted to go. We wanted to be able to expand regions, run all sorts of simulations, quickly modify and run scenarios that management might want. So there were quite a few problems with the code, and again, I want to make it clear that I'm not ragging on the data scientists who built this. They were brilliant and built just the right solution at the time. But as things grow organically, there's a decay, right? So unit testing in this big monolithic script they had ended up becoming difficult. Documentation was unnatural, sort of unenforced. Modularity, not particularly there. It's all sort of big scripts that you can kind of loosely couple together, or fairly tightly coupled together, actually. There's no real data catalog, so to figure out, you'd have to do a lot of grepping, look at like 7 places this column was modified. To debug, you had to run the whole pipeline. There was no way to just like run one column and see what happened. And to do data validation, you're just like running some last minute things on the table you generated. So the perfect initial solution to forecasting problem was probably like one script at first that solved the thing quite well, plus a lot of time, 3 or 4 years, ended up being spaghetti code. And what happens when you have all of these problems and you want to start expanding your models into new regions, right? You want to say, okay, we're in the US, we want to really start forecasting in the UK. That's where citrus is going. You want to add complex scenarios on management plan. They're like, what if we up the marketing for this specific part of the business? And you have a data bug and very little time to solve it. So because of those previous things. So the answer is this wasn't fun. They were kind of drowning under this. And I want to say, as a note, this is not actually a unique experience in Stitch Fix, time series forecasting, or even pandas. It's just a pretty general thing, right? You start with something, people keep asking you, and the pace at which you have to improve it, have to make changes to it, is faster than the pace at which you can keep it happy and scalable. And that's sort of like scaling your team component. So this is the big problem we're trying to solve. I don't know about you, but I can relate to this. I don't always write complex data pipelines, but when I do, it's always an unintelligible mess of spaghetti. So, likely Hamilton. And I hope you guys don't relate to this idea. They're all better at writing cleaner data pipelines than me, but it starts off in a Jupyter notebook, copy a bunch of code, data frame manipulations, get to production, call it a day, kind of about somebody else. All right, the solution here was Hamilton. I'm going to talk a bit about that and how we sort of solved that problem of enabling you to scale the pipeline without making it messier and messier. So the aha moment, the sort of first, the thing we thought about that was the sort of driving innovation for Hamilton is pretty simple, actually. It's what if every column, so in this case column, but it could be more than a column, it could be just sort of Python objects, sort of artifact from your data frame, or from your data set. What if every one of those corresponded to exactly one Python function? And what if you could determine the dependencies from the way that the function was coded? So in Hamilton, the artifact column, in this case, is determined by the name of the function. And the dependencies are determined by the parameter. That's the core principle of Hamilton. Right? And if you've seen PyTest fixtures, or Dagster has software-defined artifacts that came out after this, after we open sourced it, it's a similar idea, right? It's this self-containing notion of here are the dependencies, so that you can get everything you need to know from a function. All right, so what does that look like? Instead of writing it in this old way, where you're doing these sort of like simple manipulations on data frames, messing around with columns, you declare it in this new way, right? So we've got, okay, dfc equals dfa plus dfb. dfd is some transform on top of dfc. Instead, we're declaring c as a function. It depends on a and b. You add them together. And then d now depends on c, and we're transforming it, right? Simple. It's pretty easy to see. Again, Hamilton supports all Python objects. We're going to say mostly data frame series for now, but it's very general purpose. So outputs are equal to the function name, and the inputs are equal to the function argument, right? Does it make sense to everybody? Simple? Cool. So what does the full hello world look like? Like, how do you get this stuff running? It's this much code. You've got your functions, and you've got your driver. And this driver is the piece that actually tells you sort of what, when, how to execute. The function just tells you the business logic. So this decoupling of the driver from the functions is pretty key. What does the driver look like? Well, import the driver and import our functions. Right, we've got feature logic. Instantiate the driver, pass it some sort of initial data or configuration. I'm not going to dig too much into how this works, but there's a lot there that Hamilton provides power with. Execute your data frame. So actually run it. In this case, we're going to run C and D and print the result. We'll get a data frame with C and D, and that's it. Right? So, TLDR, for each transform, you write a function. Functions declare a DAG, a direct acyclic graph. If you know what that is, great. If you don't, that's totally cool. I think the point of Hamilton is you don't really need to know the fact that it's a DAG. The DAG is just a way of sort of representing these compute flows, data structure, and Hamilton handles the execution of that. So we got our feature logic, we've got our direct acyclic graph, and we've got our driver, and together this makes up the Hamilton pipeline. This makes up your data flow. All right, so there's a lot more to Hamilton, and I'm not going to go into all of it today. But the big question that people initially say is, like, doesn't this make your code more verbose? Not only are you writing functions, but you're also writing a single function for every sort of column or every output in your data frame. What if you have a lot of them? And the first thing I push back is like, yeah, I agree. I'd say that's actually not always a bad thing, right? Verbosity is not the end of the world, especially if it's a trade-off for sort of like cleanliness and management, which I argue that Hamilton really is. And you get all these benefits I'll go into in a bit. But when it is too verbose, we have a bunch of decorators to sort of add metadata and express things in higher level functions. So if you look earlier, we had this notion of assignment, right? So DFA equal DFA equals CFC. That's the sort of basic construct of writing functions. And then we have the easy ways to sort of represent other higher level programming constructs. So tag is just attaching metadata. Parameterizing, this is doing currying, so it's kind of a for loop, right? For loop setting a value. Extract columns takes a data frame and represents it out into multiple series, one node for each series. Check output is data validation. Config.when is kind of like an if else. It says so it essentially uses all the time for regions, right? So if use this transform with these dependencies, if the region is US, if the region is UK, use these, right? So you can start building code that is both readable and very dry, don't repeat yourself, but sort of gives you this sort of real inspectability and real power into it. And we're adding decorators all the time. I'm happy to talk more about them. This is like my favorite feature of the library. So to summarize, Hamilton forces you to write transforms and Python functions in a certain paradigm. And these Python functions provide everything you need. Unit testing is simple. You got plain old Python functions. You can easily unit test them. We haven't yet, but you can easily generate sort of like unit testing stubs to get you started. Documentation, use the docstring. Easy enough. Modularity, everything is by definition into small pieces, right? So function. And the functions are organized into modules. So there's a sort of natural like hierarchical modularity that you get. To make a data catalog, you can look at the code as a sort of central thread your definition store. So instead of searching through your data, you're searching through the definitions of your data, which will correspond to your data. And all you have to do is look for a column name if you want to figure out where your artifact came from. Debugging, you can execute functions individually or at breakpoints. One of the really cool things is you can say, this piece looks weird. There's a quantitative mess right here, but everything else looks good. I'm just going to run all the upstream pieces instead of rerunning the whole pipeline. And you got trustworthy data. So data validation is included out of the box. And we have all sorts of things. I'll show you exactly how that works in a section later. So decorators provide sort of powerful higher order operations to make this less verbose if you're not a fan of verbosity. And the driver allows you to decouple the transform definition from the execution. Right, and at Stitch Fix, it's been running in production for 3 years now. I guess I'm happy with that. The initial use cases managed is 4,000 plus, probably 5,000 or 6,000 features by now. Our data science teams love it. But that's just the initial use case. We have a few others that we've onboarded. We've enabled the monthly model and feature update process for them to do it 4 times faster. So that's a big win. It's just a much simpler process now. It's easy to onboard new team members. They can, this code is just natural to read for people who haven't even seen it before. Code reviews are simple. You can see sort of the changes in functions and understand how your data and the way it's created has changed over time. They finally have unit tests, and we actually auto-generate Sphinx documentation for them. So they have now their entire pipeline documented when they press a button using these docstrings. a little visual. On the left is, you can see, I guess I'm still, so we helped them write it initially for this use case. I have written the most commits, because I'm like a small commit type guy, but Jason there has written far more lines in this than I have. He's a big commit type guy. So this is what I wanted to show from the left side is that we've been sort of handing it off and working with the data science team very closely. They really like it. On the right side, this airplane is a visualization of a part of their DAG where it's colored according to like some sort of tags they have. So it's a really fun one. All this is to say is that it's just like really complicated, but it's a slightly simpler, sort of slightly nicer way of visualizing it, and they've done a lot of other work sort of visualizing and understanding how it works. I think we found the diameter of this DAG is like 15, which is pretty steep compared to what I've seen. So, any questions about Hamilton before I jump into scaling out feature engineering? Yep.
It seems like you could do like other things like feature engineering. Like if I have some, ML training routine that I use all the time, that would just be something that gets into that, right?
Yes.
So this is really just, it's a really nice way of building that.
Yeah, it is. Our first use case was feature engineering. That's what I'm talking about. But yeah, we even put it in a web service at some point, right? You can say like, okay, the request is coming in. We have an asynchronous driver that ran it, so you can do like Python async and optimize it. And people have done some pretty crazy stuff with it because it's really like a nice way of building DAGs. The higher level functions we have on top of it and towards like feature engineering and model creation as well. Yep.
I assume you get the visualization of your DAG, like out of the box.
Oh, so yeah, the question in the last one was, can you do more with feature engineering such as model creation or anything? Yeah, so visualization?
Yeah, I assume you're able to visualize kind of like your data pipeline.
Yep. We've got a visualization feature in execution. I might show it later, but it's also pluggable. Yep.
If you want to return more than one thing from a feature extraction, more than one output, more than one column, presumably.
Yeah, so if you want to return more than one output, more than one column, more than one data frame, again, it's a pretty general purpose DAG framework. We have the notion of this driver decoupled from the way you define the functions, so you can kind of do anything you want. We have some simple ones to get you started with the base use cases, but it can easily get more complicated. And if you don't want it to join it in the data frame, we have a way to just like get a dictionary of results and you can join it yourself. Yep.
If maybe this is what the DAG is for, but if, for example, in 100 of the columns that you're generating out of however many thousand, it involves merging two data sets, is that something that can be done once for all 100 of the columns that it will generate, or will that merge happen every single time?
Yeah, so the question is if you're doing a similar operation such as a join for everything, will it run 100 times at one time? I mean, that actually depends on how you set it up, but the incentives are aligned to make it only happen once, because you can have that, you can define that as a singular node and have everything depend on that.
I would say there's two more questions.
Okay. I'm told that one more, and then we're.
Sure, yeah.
All right, one more, and then it all depends on the end.
How do you use scikit-learn pipelines with Hamilton? It's like a missing value imputation or one-hot encoding. That's something you would do afterwards or after Hamilton?
It could be part of Hamilton. It could be done after Hamilton. I would say that scikit-learn pipelines are like a pretty nice low-level construct. You would fit it generally within a Hamilton function, or break it out if you have sort of reusable pieces of thing. All right, save your questions for the end. I'm told that I'm moving too slow, so I will. So I'll get on to the next piece, and then. But remember that I'm happy to answer them. I'll be around afterwards. All right. So let's talk a little about Hamilton and feature engineering. Again, as we said, it's not restricted to feature engineering, but this is the area that we most use it for. Let's looking at the machine learning. This is something I think about a lot. So one of the machine learning platforms here at Stitch Fix. You got featurization, you got training, you got inference. Let's focus in on featurization. That's loading data and transforming into features. And again, you can model the entire ML workflow in Hamilton. We did in the initial use case, and I've seen quite a few others that do that. We're going to focus on featurization. So Hamilton works for any Python object type. I'm going to try and drive this home. And the cool thing is it's embeddable around anywhere Python runs. So orchestration systems such as Airflow, Kubeflow, Metaflow, Prefect, Flight, and Dagster, it's already trivial to integrate. So all you have to do is run your Hamilton pipeline within a step there. We have other ways of thinking about integrating too, and web services. So to model featurization, what do you need to write? Well, you've got to write your functions to load data. You've got to write your transform and feature functions. and then your driver to materialize data, and you can execute only what's needed. So load your data. This is extracted in ETL. Transform it, create your features, write your driver to materialize it. There's data loaders, feature functions of the driver, and execute just what you need. So you need that block one there, let's get all the yellow ones above, and the loaders. And so, okay, pretty simple. This is how you do it in Python. Why is this hard generally? I want to say the answer is scaling. It's a cop-out answer because scaling describes everything. Like scale, it's cool. And we'll do the love scale. So scaling, and again, what do I mean by scaling? Well, I want to talk about scaling in two different ways. So the one that I'm really interested in, I'm curious to see if you all are interested in as well, is the notion of sort of scaling to match human and team challenges. So Hamilton is meant to solve this specifically. This is handling highly coupled code, difficulty debugging and understanding data flows, messy collaboration on complex pipelines, and validating your data. Hamilton was built specifically to solve this problem. But obviously there are the compute challenges. Not everybody has small data that they can run on their laptop. So data is too big to fit in memory, or they have a bunch of parallel computations they want to use, and Hamilton's not going to leave you out to dry there. Hamilton has integrations for this. And the power of Hamilton is that it provides a decoupling layer. So you can decouple the scale of your compute, the scale of your compute from the actual functions themselves to a decent extent. All right, so how does it help scale the human and team component? Also, let's talk about it. Hamilton can help you decouple code. So you decouple code from the infrastructure. The driver handles the execution, and the functions themselves handle business logic. So there's a natural decoupling within the code. And as you can see, you can run these same modules in a bunch of different drivers, depending on a bunch of different driver configurations, depending on how you want to run it, right? And what sort of different ways you want to run it, and what platform you want to run it on. And decoupling code from itself. So code is organized into functions, functions are organized into modules, and the functions actually don't know about Hamilton, right? They're just plain old Python functions, so they're portable, reusable anywhere. If you run all your Hamilton code and you're like, yeah, I don't like Hamilton, but I like my functions, you can copy them over and write your good old procedural stuff. Aside from a few specific examples, but it's all pretty portable. Right, Hamilton makes it easier to debug. So to sort of knock your bugs out, you can just rerun the broken paths. Python functions makes it really easy to do unit tests and natural debugging. Hamilton gives you runtime data quality checks for free. I'll talk about that in just a minute. And it allows you to quickly mirror the search space of data bugs. So if you've ever had to deal with a data bug in your pipeline, like some weird thing that cascades down, you can do a binary search of the DAG, and you can also see, like, you're good to do like a bisect over the shape of the DAG and like do the binary search over like all these different spaces. And it helps understanding and visualizing. So you can visualize the data flow and execution path. This is getting at that question you asked earlier. Here's like the actual DAG, one of our like hello world examples. And you can clearly track dependencies as well. All right. Natural collaboration. So Hamilton serves as a central feature definition store. But what I mean by this is that everything is grepable, and you can figure out the way it's generated from the name of the artifact. Well, this is an interesting thing where it forces alignment on naming. So if your function is declaring an upstream dependency, then those two have to be the same name. So you're going to start thinking more. You're going to see this name above and start thinking more about how to name it. And this is really fascinating because naming is the hardest problem in computer science, and everybody who compares it to the naming problem, that's why problems are named pretty hard. That joke works anymore. But documentation is included in natural Python docstrings, and you can minimize conflicts when collaborating because everything's sort of localized to the specific business logic you're working with. Nothing's spread out. Change management, feature versions are in Git, all the changes are in Git history, PRs are easy to read, you can really trace their changes back to the functions. So I want to dig in a bit how we handle data validation, but the big problem that we see is garbage in, garbage out. Right? So if at any point in your pipeline something's looking bad, then the whole thing falls apart, and it doesn't matter how well tested the latter stages are if some piece of the early stage is broken. So yeah, how can you build reliable pipelines if the data is bad? The answer is obviously you can't. It's going to be a bad pipeline. The solution here that we've come up with is runtime data using a runtime data validation decorator. So you can see here, I hope this makes a lot of sense just looking at the code. This is some data we care about. We say okay, data type's going to be float 64, range -1 to 1, allow nans not allowed, and importance is born, so it doesn't actually fail out, but it'll print out in your pipeline execution. We're sort of working on callbacks there. So we have a few basic checks. That's what I showed: range, nan check, valid categories, it'll output them like a ton more, and that's sort of a nice pluggable framework that we can add to with open source contributions. And those are for pandas and primitives, but it's highly pluggable. We want to like expand this out so it works with a bunch of different things about different execution frameworks. And then there's something more powerful. If you guys are familiar with Pandera, I think that's Nils Vandelan's project, which is kind of taken off. Pandera and Hamilton form like really nice, powerful checks. So you can give this whole data frame schema for your data you're loading from the warehouse, and then it'll fail with the beautiful errors of Pandera. And it's like super extensible. I probably err on the side of making my code like overly extensible. So you use a base class, you can write your own, you can do whatever you want, and we want to add a lot more. So we want to add integrations for any type of data frame, data type, IDIS, polar, whatever, and add multiple data validation frameworks. You can imagine great expectations, DQ, we talked about Y-log scopes, and the sky's the limit here. We're at all prime validators, that's the only sort of fun example I can think of. And it's just a really fun algorithm. All right, so to sum it all up, why I think this helps with the team scalability component, I want to share some code. And the goal of this is that you should be able to look at this code, and if you're familiar with Python, this should be fairly obvious what it's doing. If you're not, though, like my goal is to get it so like anybody can read this, right? In a way that Python did to programming, where it just became like that much more English and that much more readable. I want this to do for like Python and data. So what this says is feature client at normalized, owned by the client recommendations team, contains no personal identifying information, is of type float, depends on 2 upstream features, has no NaN values, and produces values in that range. Version control system can show you a change over time, and grep the code base for downstream dependencies. All right, so I hope I bored you with the scaling community component that I'm really excited about. And if you're looking to sort of get to the big data side, we'll get there in just a second. So how do you scale the compute and the data using Hamilton? Well, a few different approaches, but the main approach here is to delegate. So we have some pretty extensible ways of doing this. I want to talk about how we've integrated pandas with Ray and Dask for parallelism, and with Hamilton with Ray and Dask for parallelism, and pandas on Spark. But there are a lot of different directions we're going here. So this one's sort of a call to action. Ray and Dask allows you to run in parallel. They also phase this is sort of the parallelism side. Take a single machine, scale it up to multiprocessing, and then scale it out to a cluster. Pandas and Spark allows you to scale horizontally for data set. This used to be called koalas, and they integrated in Spark, the Python Spark is right there. And switching only requires changing, switching should be easy. It should only require changing driver-side code, and except for Pandas and Spark, which requires changing a little bit of the data loaders component as well. But pretty simple and pretty modular. So scaling with Ray, here's our basic driver that we're looking at. This should be familiar from earlier, or something like this. So you've got our data loaders, our date features, and our spend features. These are sort of like dates, like holidays and stuff, and then spend features, marketing spend. And we execute it, save it out to the database, so ETL. What does this look like with Ray? Well, we're importing the Hamilton Ray thing, initialize your Ray client, create this graph adapter piece, which is a powerful abstraction that can tell you how to actually execute this and how to sort of crawl the DAG and run it. We can then join it all together as a pandas data frame, and we've got this, and we pass that graph adapter into the driver to run. Finally, shut it down and give resources back to your friends. Right. What does this look like with Dask? We can import the Hamilton Dask, same deal, create a Dask client, pass that into the Dask graph adapter, pass the Dask graph adapter into the driver, run your stuff, shut down the client, and give the resources back to your friends. And pandas on Spark. So again, this one's the one that's a little more complicated because the data, the like object of the data types is going to be slightly different for this, especially for the initial pieces. But what we do, create your Spark session, etc. Create your Spark graph adapter. You want to pass it a spine in this case, so we know an index to join on. You've got your driver, which takes that in, and the only difference is now it puts in the Spark data loaders instead of the pandas data loaders. This is so you can get in the right object, so it can sort of work downstream. The cool part about this is you're only rewriting that one little piece, not the whole thing. Because the koala data takes over. And we're looking at sort of mode-in integration as well, which will solve a similar problem in a sort of easier way, whatever. And finally, stop the Spark session, let your computer clean itself up. So how does this work? We've got our functions, we've got our driver, and we then create our DAG, same as usual, and we end up delegating through Dask. So it's actually this simple, right? Asynchronous callbacks remote and Dask delayed allows us to sort of crawl the DAG, writing it there, and running everything we need in parallel. All right, with Hamilton and Spark, how does it work? Same deal, except you change it to be the Spark pandas equivalent objects instead. Spark will take care of the rest. Run it, we then sort of like submit it to Spark and like run it on top of Spark, should be good to go. So we're pretty excited about this, but definitely some caveats. For serialization, you use the serialization methodologies that delegate to the underlying frameworks. For memory, the default should work, but fine-tuning at a function level is not yet supported. Python dependencies, you need to manage them. That's kind of obvious. We're really looking to graduate these APIs from experimental status, so contributors are wanting to help extend support in Hamilton. If we have just the right paradigm, we want to make sure we're keeping up to date with the sort of PyData community and best practices to scale it. So it's like talking with Jeff about IDIS and how that fits into the stack, and I think Hamilton is sort of poised to do that, but we want contributors to help us get there. All right, so to wrap up, let's talk a little about open source progress and next steps. All right, open source progress. It's in early stages of a very thriving community. So multiple high-profile users. We got IBM, UK Government Digital Services, the British Cycling Team, which is awesome because I'm like a cyclist, I really like that. The Federal Reserve, Pacific Northwest National Laboratory, Stitch Fix, and a bunch of others. 670 plus stars on GitHub now, a growing set of core contributors, and we're looking for more contributors, bug hunters, user feedback. So anybody who's interacted with it, that's going to give us sort of value out where to take it next. I really believe in investing in open source and sort of allowing like things that benefit your company should also benefit the world. And what's our vision for this? Like, where do we want to get it to? So I think it can be the unifying layer for machine learning ETLs. I want to be able to compile to an orchestration framework. So you might be familiar with Dagster. Prefect is talking right over there as well, in one of the rooms. Next door, Apache Airflow, Metaflow. No reason that you couldn't write an API in Hamilton and use the like really clever underlying orchestration mechanisms of these to execute it. And you can even be writing your entire set of functions and sort of break the DAG in just the right way to break into like Airflow pieces or Metaflow pieces, giving you a really clean API and a portable execution layer. And this isn't even counting the other ways of running Python, so like IDIS, pollers, etc. I think there's some nice integration there as well. We're going to be integrating with data quality vendors and open source options. So you've heard of Arise, it's more of a sort of big company thing, but YLogs I'm really excited about. It's just a very natural thing to like integrate that with data quality. We met with them, we just haven't done the work to do that yet, but that's something we are planning to do along with contributors. We want to be able to trivially load from a variety of upstream sources. So get your data in from Snowflake, get your data in from DB, and then add SQL support, right? So I personally believe most of the stuff you want to do, you can do in Python. But there are some things that are very SQL required, and DuckDB is sort of like really cool because you can bridge the like Python pandas SQL gap there, and you can have transforms, you can have loaders in DuckDB, quickly go over to pandas. So we want to be able to add that too as well and make it so that you can kind of like DBT add a SQL node in. It's a Python function that perhaps returns a SQL string that we then templatize, and we can run your SQL. And how are we getting there? So we're adding new decorators all the time. I'm working on one now that can reuse a subdag. So if you have some big sort of set of functions that you want to run for like 5 different configurations all in the same DAG, I managed to enable that in a way that's nice and readable. More natural SQL support, as I said, and please come up with ideas. Here are some on the right about people who have sort of ideas of what to do. In this case, we're figuring out how if you have like 1,000 features, not to add 1,000 dependencies, but instead sort of collect them all into a data frame. And more informative execution. Obviously, more visualization of data, that's just an inherently hard problem. Compilation and data flow specification, that's sort of what I was getting at earlier. A nice user interface, perhaps, and more ideas we would love to get. We'd open up tickets. And so, yeah, give Hamilton a try, we'll your feedback, give us a star on GitHub, because you're paying like 10 stars. Great about issues, join from Slack, we have a nice Slack community. You can also follow us on Twitter. I'll find a way to share the Slack community out with PyData folks and all of this stuff. I'll get these slides after a little bit. And yeah, oh, sorry, this was a reminder. She came up to me and was like, "Oh, you guys can eat in the room because it's going to be crazy over there." So I added this in, but it's this even reminder because I did it literally the last minute. And thank you. If you have any questions, I'm here now. I would love to answer them. You can yell at me online on Twitter, connect with me on LinkedIn, share with me on GitHub, and use my email somewhere. Thanks, folks.
Cool. That was awesome. So we'll probably have more questions. Let's see. We have 5 minutes for questions. So let's go over here.
And I'll be around afterwards too.
So let's say I add a column. Is there any way you can actually backfill it without any data leakage for training? And the second part, and the second question is, let's say I add 2 columns.
Mhm.
Is there any way they can go on different schedule? Like one can be a daily and the other can be weekly and something like that.
I was going to answer the second one first because that's an easier question. Yes, you can run sort of different drivers on different days, right? So it's a configuration that you have in the execution mechanism that you pass in. You can choose what to run, and then you can run that different ways. In terms of backfilling, I would say Hamilton as it currently is like slightly lower level. So I would love to, I'm pretty confident that we can figure that out. It's a matter of how you merge in, and then the data you pass in, and the configuration to make sure you can do it, because it also depends on the validity of the upstream data you get, whether you get any time leakage. So Hamilton is slightly lower level, yeah, you can probably do that.
Great presentation, thank you. This may be kind of an obvious question, but what happens when, so you show the checkout to decorator and
Yep.
say you provide a range of values for the parameters. What happens when the range is violated? What happens?
So yeah, you have 2 choices. There's failure and warn. So either it logs an error, and you can read that out in your print statements. I think we're adding the ability to do callback soon, so you can add it to the callback. If you select fail, then it'll error out. Right now, I think it'll error out when it hits that at first, but no reason it shouldn't error out at the very end of the pipeline as well. So you can choose.
Any other questions?
When you started with SwitchFix, did they hire you specifically to be an open source developer? And what's their motivation for open sourcing stuff that they're putting all their own resources into?
Yes, they did not hire me to be an open source developer specifically. They hired me to build out their machine learning platform. And we have a bunch of blog posts on that. The motivation is twofold. The culture is very open, and there's not too much secretive, so there's high value, and you can get a lot from the outside world. There's also obviously branding, which is big. Recruiting, that was a big thing since we started. And also my personal motivations. I love doing this stuff. So, of course, they hired me as a developer. It's a good thing I would never just get.
Hey, what do you find is typically the dividing line in Hamilton of, what's reasonable for a data scientist to kind of write in the course of their normal model implementation or feature engineering versus stuff that more like data platform engineers or an ML engineer might, I look at some of the decorators and the addition of metadata, where do you find that divide? Because I see parts that are super approachable or that data scientists think about, and maybe stuff that I'm that makes sense, but I would never have thought about it.
So I think the goal is to make the entire API very data science friendly. I don't want there to be anything in there that's complicated. The piece that is complicated is when you start to get to the driver and the execution code and plugging it into your infrastructure. I think that's where you'll need more of an MLE or software engineering platform type background, but that's also what we want to add into the framework itself.
The question about so during the inference, how does Hamilton help you, or is there a way recommendations for speeding that up on the inference side when you have to do feature transforms?
You mean so? I see this question going in a few ways. Do you mean when you have to rerun your feature transform pipelines in an inference setting and executing, or do you mean actually the model inference speeding that up?
Yeah, like you have a user request that contains some features that you want to transform using Hamilton kind of functions. Is there a way to, is there any recommendations to speed that up?
Yeah, so in terms of optimization, literal optimization, we can delegate to the underlying frameworks, but Hamilton's, it's all sort of portable code, right? So this is built for ETLs, but easy to sort of take and stick in any sort of context you want. So you can say like, okay, I have this big complex transform. Here are where the features comes in. Rerun that DAG in production in your microservice where you're storing your model results, and have another node that's actually the model, right? So like load that, have a person that loads the model from a cache, have that node cached, and then have it pass all the way through. So it's definitely doable to do that. We'd love to see sort of open source using that sort of thing.
Cool, awesome. Let's thank our speaker again. Next up in 5 minutes.